Hey, good afternoon, everyone. Good to have you here. Our last day of new content before the exam. So I thought I'd take you on a little tour of a few things I've updated in Canvas. So we're going to look at 12.5 related rates. Again, the technique is not something new. It's going back to implicit derivatives that we did in 11.6. So these things will tie together. There's still the extra credit 12.6 elasticity that will be open all the way to the end of the class. So if you want to put that off till later, that's fine. I have a couple more. There is a lecture in there, and I have a couple more resources I will post in there that might help. But what I did this morning, I think I had it further down, but anyway, from a previous semester, I have summaries on each of the sections we've done from 11.4. There is a PDF, which is basically what I got from doing the video. So it's a printed version of the summary. So there's a summary at the top where I review a few of the important things, and then I do some of the practice test or the test review questions. This one is the PDF. It's already done, so you might want to just look at it, and if you can follow along. If you like to see it sort of in the live version as it's being done, that's what the video is for. So I video it, have it recorded, and I've got that for each of the sections. So if you've got any section you're struggling with, you might want to come here, take a look. But it'd be a good practice to kind of go through each of these sections. Some of the videos are 20, 30 minutes. I think one of them was almost an hour. I can't remember which one, but you could figure that one out. But they kind of take you back through the video. I try to be brief in the summary part, so get the lecture down to maybe 5 to 10 minutes, and then I work a lot of the sample problems. There are also, let me come back here. I left this in here. I have a video solutions to WebAssign problems. This go back probably 2 years. We don't have them in now. They used to have a review in WebAssign, but I put that there. Maybe it might be helpful for the homework or anything else. So use it as you want. And this last one is the most current version from summer of the exam review provided by the coordinators. It'll be very similar to the one above. There may be a few slightly different questions, but again, you could use either one. I am going to look at the most current one to see if there's anything that we should cover separately, but it should probably be mostly very, very similar. In fact, identical problems for a large part, maybe a few extras. So I'll just make sure everything's covered. It might actually be more condensed, but we'll take a look at that. I did just, while I was waiting outside, I got that email that sent the actual exam, so I can review that and make sure that the resources here are everything you need. And so on Wednesday when we meet, that's our review day, I will highlight specific things that you will definitely want to take a look at, and we'll record that. Any questions or concerns before we jump into today's content? Okay. So this is related rates. If you think back to what we did in 11.6, we were taking the derivative of both the x and the y variables. We had two variables, and we used this specifically when we weren't able to solve for specifically y equals something in terms of x. We're actually going to have three variables, but one of them's sort of invisible. You won't see it in the equations, and that's time. So things are happening over time. We have a circle. The radius changes over time, which means the area changes over time. So those are two different variables, the radius of a circle and the area of a circle. They change differently. Those are two variables. But since they're changing over time, the derivative is always with respect to time. But you will, we'll go through here, but generally we'll never see the variable t directly in there. We just know that it's happening over time. Okay, so we still use our derivative, but this time we'll actually have two markers. So they'll be like dy dt and dx dt. We may use different letters, but there'll be two variables that are changing over time. So our derivative is that variable over time, this variable over time. We're given some information and we're able to go forward with it. Okay, so that's, just look for that invisible, what I call the invisible variable. So we'll walk, let's see, let me, always forget to get my writing tools set up. Okay, there we go. Okay, so that's what this is kind of saying, that we're going to be given something, some kind of a variable. They just call it Q, whatever it could be. Again, a lot what we deal with is area and the radius. But there are things that are changing over time. So we'll take the derivative of the quantity over time. So you're going to look for, again, the two main ones is example of using area. So dA dt will be one of the variables we have, and again, it's a rate. Remember what a rate looks like. It has it has two units, something per something, and so usually it's going to be area would be square inches per minute or something. So there'll be time in there. The other variable, as I mentioned, oftentimes will be something like a radius, and we are oftentimes given the rate that the radius is changing, and we're also given a particular time when the radius is a certain amount. So we have to kind of come up with the equations. So this also takes back to, I think one of your favorite sections was probably 12.2, the problem solving one. And I'm joking, there was probably everyone's least favorite one, right? But you're going to see some of that same sort of problem solving. We have to set up a formula, so it's going to involve volume, area, and such. Sometimes they give us a hint. They say this formula is such and such, so we'll go from there. Okay, so we'll kind of walk through this. It'll make more sense once we do it. So as we go to solve it, we're going to identify which quantities are changing. And again, they should kind of pop out at us. They're talking about area or the radius or something in that terms. They may be talking about, there's a couple questions towards the end we'll work that are average cost. And in average cost, what changes? The amount, the number of items made, so that's one variable, that's our x variable, and then the average cost changes, that's another variable. Okay, so we kind of list those. We restate the problem with those rates in there somehow, so we've got to take a derivative, and we go through that. We look for a relationship, and sometimes we're going to need to draw a diagram. Again, if it's a circle and radius is changing, it's helpful to kind of draw it out, label it. We need to find equations that relate to that kind of change. Sometimes we're given it, sometimes we're given the average cost. Again, if it's the area of a circle is pi r squared. Circumference of a circle, 2 pi r. So we're looking for those. Okay. And then we take its derivative, and so we'll have the values of the variable, we'll have the values of the rates of change as well. And again, we'll see how we do that. Then we substitute the solutions and solve for the derivative as required. Okay, so I'm not very good at step by step, but that's kind of what the textbook laid out. This is how we go through it. So let's do one together, And then as I've gotten the textbook, I left their solution slide by slide, and we'll kind of review it. But in one slide, we can kind of do all of this. So first we read, what are they talking about? The radius of a circle is increasing. So we look for words that indicate change, rates, right? Because that tells us something's increasing. So there's a rate, and they even use the word rate, 10 centimeters per second. So I'm going to circle this. Seems like the radius of a circle, since it's going to vary, that should be one of my variables. We'll just call it r instead of x and y, right? So we're going to have a variable r. We have a rate, and so this is a rate that relates to the radius, right? A rate is what? It's not the variable itself, but it is the derivative of the variable, okay? So this rate here that they give us is dr dt. So the derivative of the rate of the radius over time. Okay, so whenever you see rate, you know you're going to have, that's going to refer to a derivative. And sometimes it's like, in this case, it's a constant. It's not, that has no variable in there. Then the question, how fast is the area increasing at the instant when the radius has reached 5 centimeters? So we're introduced here in this last sentence two different things, that we also have something called area that we're going to be interested in. And the question itself is not about the area, but it's about the derivative of the area. So we know we're going to have this involved. And then we've got sort of a particular target. At some point, the radius is going to be equal to 5 centimeters. So I kind of just do this. So we've got a few things that we already know. The radius equals 5 centimeters. The derivative of the radius is equal to 10 centimeters per second. We know the radius is increasing, and we know the area, or at least they're asking about it increasing. So how do we relate a circle to its radius? A circle's area to its radius. The area of a circle, I was going to go with 2 pi, but that's a circumference, right? Oops, I just erased everything. Well, we'll see how we do. Area is pi r squared. Right, so that's something that's always true. So we got these geometry things. That's going to be our relationship between the radius and the area. Okay. To solve everything that we need to do, what we're going to do is we're going to take the derivative of this over time. So what's the derivative of a? Area. A as a variable, right? It's just 1. Just think of it if it was a y, right? It's just the derivative is 1. But we put this marker that we took the derivative of area with respect to time. And notice how there is no variable t in this that we're starting off with. It's that invisible variable, but everything is changing over time. So there's that sort of underlying variable. And so this is implicit derivatives, right? So we took the derivative of the area. That's that. Pi is a constant, right? So we're on the right side now. What's the derivative of r squared? 2r to the first. So we took its derivative, but we took the derivative of r, so we need a marker saying that we took the derivative of r, so we'll say, okay, that's dr dt. And that's just from implicit derivatives. And again, it's something a little new because we've got this invisible variable t. Okay, so you just have to remember, every time you take a derivative on these things that are changing over time, you're going to have the variable you're taking the derivative of with respect to time. And the variable time itself actually sort of never shows up, right? So that's what we're done, sort of. Now, do you see where we could start plugging in some things, right? The question, how fast is the area increasing? Well, that means we want to find what is dA dt equal to, and we're actually all ready to go. We've solved for dA dt. We have over here 2 pi r. Well, r, what time do we want the areas changing? When the radius equals 5 centimeters. So we're back here. We could go, we can actually plug in 5 for r, because that's the time we're interested in this time. What's the rate of change of the radius? Well, that's what they gave us up here, and it's a constant rate of change, so 10 centimeters. And again, you could put units in here, and you'll find that they'll cancel out, or they'll do whatever, because this is 5 centimeters. Let me go ahead and do that, and then we're going to multiply that by 10 centimeters per second. What you can see is that we're going to get centimeters times centimeters. We will get centimeters squared per second, which is units of area, and that's what it's going to be equal to, right? The derivative of area with respect to time is now 2 pi 5 10 centimeters squared per second. So 5 times 10 is 50. 50 times 2 is 100. So this is going to be equal to 100 pi centimeters squared per second. And again, you don't have to necessarily have these units, but by putting them in there, doesn't it feel a little bit more confident? Yeah, that's area, and it should be square units. Okay. And we're done. Now we're done. We've actually got our answer. Now you could take 100 times pi, because pi is 3.14. I think the answer, I think they go on to do that. That's 314 point something, right? But if centimeters squared per second. So we could write it that way as well. 100 times 3.14. The decimal, yeah, I think 314. So do you see, does this look familiar, thinking back to the implicit derivatives? Maybe. Or was that one that you skipped over and said, I'll get to that later? Well, now it's later. Okay, so we'll do some more of these. But that's our answer. What I'm going to do is I'm going to click through, or if there are there any questions? We okay? Yes. Here? Okay, so then from the red, I'm substituting in the numbers, the 5, and that this is 10, and then I just multiplied 5 times 10 is 50, times 2 is 100 pi, and then if you start pi is 3.14, multiply it by 100, you get 314. Okay, and this is, yes, sir. I will accept either one as far as for final answers. The thing is, you have to recognize on a multiple choice, you have to be able to pick the right one. They may have one or the other. So be able to see which one they do. But if on an open answer, both of them would be acceptable. Personally, I prefer the 314 because I know what that is. 100 pi, I don't really have a good feel for what kind of a quantity that is. But that's, So again, this is a way you know later on, if you want, you can pull up this PowerPoint or this Google Slides and read through it. But it's basically walking or talking it through each of the things. So the rate of change is 10 centimeters per second. We kind of picked that up. So it's translating it. That's dr dt. Again, you're going to see this. Every question you're given will have two variables. You got to have the two variables changing over time. Anything that's a rate will be a dt, some derivative of the variable, and then there'll always be something of where the variable itself has a fixed point. What's happening at this particular time? How are things changing at this. Because if we don't have that, then all we have is we've got a formula that will tell us at any given time. So you'll always see that. And so, the question is, what's the rate of change of the area at this point? Had it been a different point, the rate of change of the area actually may be different. Okay. Again, we kind of just went to it. Whenever you're dealing with a circle, you're going to do with its area. Area is pi r squared. So these are things that are just pulled out of geometry. We don't get too complicated. You'll see one with volume, but that's one that they will give you if they ever use it on the test, and they even give it to you here. We take the derivative using implicit derivatives. So the derivative of area is just 1 times the derivative of area, 2 pi r, dr dt, so forth. Substitute it, and then, I was just looking ahead. I recognize that they gave the answer as 314. Yes, sir.
Like the derivative of the area pretty much looks like the circumference of the circle.
It is. I was just thinking that, and I was going to, but there is some sort of connection. But yeah, the derivative of the area is the circumference, which makes you think that, our world makes sense. At least physical world makes sense. I'm not so sure about the social world, but yeah, you'll start to see these types of things. It's kind of cool. There's probably a whole explanation for it. I'm sure there is. I probably read it at one time and then you kind of forget it. But yes, derivative of area is the circumference. Okay, and they work through it. And again, they put the units at the end, but if you go through there. So again, now we're just, there's no new content. We're just going to work several different types of examples because again, this one is heavier into the problem solving than most of the others. It's like that one we did that was strictly problem solving. Okay, so let's come back to this color. Actually, sometimes I like to go from the back because if we read the last part first, we know what we're talking about. So here's the question: how fast is the base of the ladder moving? So that's a rate, right? Something that's moving is a rate. When it hits him, if Jane is 4 feet from the ground, so there's another number. Okay, so now we need to back up. So Jane is at the top of a 5-foot ladder when it starts to slide down the wall at a rate of 3 feet per minute. So we've got a rate here. Got a ladder against the wall. We've got Jack standing on the ground behind her. And if it's starting to slide, I don't know why Jack doesn't go and hold the ladder, but maybe he just can't move that fast. Maybe he's back to it. So we've got a wall. I guess we've got a floor. We've got a ladder that's leaning against here. We know the ladder is 5 feet. We've got Jane up here at the top. And we got Jack down here somewhere. And we want to know, we've got the ladders moving down the wall. So one thing we have is we have this, the height of the ladder is going to change, right? As it slides down, the height is going to get less and less, the top. And then we have over here, sort of thinking this is a triangle, we have this base, which is the base of the ladder, and since the ladder is rigid, as the height goes down, the base is going to slide out. So as Jane goes down, the base of the ladder is going to go to the right, eventually hit Jack, and so far that's all we got. We do have, and the ladder is 4 feet from the ground. So that's a height, right? So we know at some time h is going to be equal to 4. That's what that's telling us. We've got this rate. It slides down the wall at a rate of 3. So it goes down when it's going down, this must be the rate, the derivative of the height, because that's what's changing, dh dt. See any other numbers in there? A 5-foot ladder, so that's fixed. Do you see any formulas that would help us set this up? What? Base times height. Well, that would give us area. There's something that relates. Notice you've got the walls, we'll assume, are a 90-degree angle. And there's a formula that relates the length of sides of a right triangle. The Pythagorean thing, yeah. So what we're going to do is that 5 is our hypotenuse, that we have h squared plus b squared is equal to 5 squared. So that's the formula. Simple as that. That's all. So I guess we could just go ahead and make 5 squared into 25, but I want you to see it's just all three sides, two legs are squared and added together will be this. So this is the Pythagorean theorem. So we've got h squared plus b squared equals 25. So now what do? We've got it all set up, we've got things, but how do we set this in motion? We need derivatives, right? Derivatives are action. This is static. This is no movement. I could plug in 4 here and I could find out where the height is at this particular time, but that's not the question. We want to know what the rate is of something moving. So we need a derivative. What's the derivative of h squared? Times dh dt. And again, you could have used other variables that you want, but also I look ahead and I try to be consistent with what the textbook's going to use. So that's that derivative. And then we come to b squared. What's the derivative of b squared? Right? 2 comes down. B to the first power, 2 minus 1 is 1. And then the marker, we took the derivative of b with respect to time. The other side, what's the derivative of 25? 0. And there's no variable involved, so it's just 0. This is sort of the nice part of it, I guess. So we've done this, we've taken the derivative. That's as far as the math we can take it. Now what we've got to do is go back to the story, plug in the numbers that we can plug in. Okay, so we were told the 5-foot ladder, okay, it starts to slide down the wall at a rate of 3 feet per minute. So that's our dh dt. This is going down the wall. So this, I'll circle that, this equals 3. Let's see what else we can put. Jack is standing on the ground behind her. How fast is the base of the ladder moving? So that's the question. dB dt, the base. So this we don't have something for. When it hits him, if Jane is 4 feet from the ground at that instant. So Jane is 4 feet from the ground. So that means h has to be 4. And now I got this feeling, yeah, I'm going to get stuck, aren't I? But I've done this enough that I think I can get unstuck. So far, are we good? We set it up, Pythagorean theorem, take its derivative, plug in what we know. So we got 2 times 4 times 3, 8, 24. So this is 24 plus 2b dB dt, and we're wanting, the question is saying we want to solve for this, but there's a little problem here. We still have a variable of b, don't we? They didn't tell us what b is. We could solve it. So this is b at time when the height is 4. So it would have been nice if they would have also told us that the base was something else, but what they've done is given us the time that the ladder is 5, at this particular time the height is 4, so we could actually calculate what the base is using the Pythagorean theorem. You'll see it's 3 because there's a 3, 4, 5 triangle is the standard Pythagorean thing. But if you didn't know, right, we could take 5 squared needs to equal 4 squared plus the base squared, right? That's 25. 4 squared is 16, so I'm going to subtract that, is equal to b squared. 25 minus 16 is 9. So b squared equals 9. Take the square root of both sides. B has to be 3. Okay. But we had to go back to it because we went through, and otherwise we kind of got stuck. Here's this b. They didn't give it to us, but they gave us, by going back basically to here, we could figure it out because whatever h is going to be, b is related to that. Because the ladder is not going to grow or shrink. It's going to stay at 5 feet, and it's just going to slide down, and there we go. So our final answer, we're going to plug in 3 for b, so we get 24. 2 times 3 is 6. I'll do this. dB dt. We will subtract 24 from both sides. So I'll move it up here. So that gives us 6 dB dt equals negative 24. And then divide by 6. (24) divided by 6 is 4. And actually, since it's sliding down the wall at 3 feet per second, 3 feet per minute, actually that's a little bit slower. I think what I would do is I would put the negative here because that means the height is getting lower, right? So we really should have, that derivative should be negative. That's the height is decreasing by 3. And if we do that, that makes this one sound a little bit better because we get a positive here. And the base is actually moving at this rate. It would be 4, what is that? What's our unit? 4 feet per minute when it hits jack. Okay. So far, so good. Okay. So one of the things you have to get comfortable with these is to be okay with being uncomfortable. Once you get it set up, sometimes like this one, we got partway through here and we still have a variable that, and I was a little concerned because I try not to work these in advance. I've worked them before, but I was a little scared. I go, I'm not quite sure. Oh yeah, that's right. I can go back and I can figure out what B is. I think we had this earlier on where they sometimes were asking like for the slope of or the equation of a tangent line, and remember sometimes they didn't give us the y value, for the point, we'd have to go back and get it. That's exactly what happened here. They didn't give us this B. They could have, but they didn't. But we could also go back to the original formula and get it. And that will sometimes happen. Okay, so that will sometimes happen. Ready? Yes, sir.
Would it be more efficient if you were to find all sites first and then plug it into a derivative?
You could do that. Yeah, yeah, once you start working them and you'll see, oh, this is one, I'm going to need that. When I started this, I'll just be honest, I didn't really look that far ahead. So I also, yeah, it would have been more efficient. And the next time I do it, I would probably do it that way. But then sometimes if you start jumping the gun, there's a little bit of a change. And it wasn't the time to put it in quite yet. Because we don't want to put it in here. I mean, when we take the derivative, we certainly don't want numbers in here at that time. Because otherwise, that becomes 0, right? We want to take the derivative with the variables and then plug in there. So, yeah. But yeah, if you're on the test and you see something like this with triangles, you'll probably remember this one. Oh, let me do it first, and it'll be a lot simpler. Okay. And this, again, is just the textbook kind of talking through what we just did. Let's see what they did. Yeah, they defined h as the height of the top of the ladder, b is the distance of the base on the floor. And yeah, they went right away with the rate. Since it's falling, they went with -3. I did that at the end because it didn't. The answer of -4 feet per second didn't seem to be right. So I just said, okay, what's getting less? The height is getting less. The base is getting more. So that helped me with my negatives. They rewrite it. And then they show a picture, right? They take the derivative, they put in what they know, and yeah, they jumped a little bit further before they went plugging everything in. They said, we know we're going to need this, you know, before they started plugging things in. I plug in what I know, and they say, wait, I need to know one more thing. That's what I would have did. Yes?
So why would you set it equal to 0?
That was from taking the derivative. Remember, it was equal to 25.
Oh, right.
Right, so they took this, the implicit derivative here, take the derivative of 25, you get 0. And that's why I like to do it on one page, because if you go over to the second page, it looked like, oh, they just set it equal to 0, but they took the derivative. Okay, we good? Again, we'll just look at a few more examples, maybe just one more. Let's see, actually they did the same thing I did. They plugged everything in, at least if you go through here, and they said, oh, we still need B. They solve for B. And then 24 divided by 6 is 4. And again, I got a -4, but I said, wait, let me see my directions. The other one's getting less. So I, you know. Okay, so I think we've got, these are coming directly from the homework. So they'll get you a good start. You may have slightly different numbers, but we'll go ahead and do this one. Hopefully it's legible. But again, it's one of the ones from the homework. I'll just highlight what we have. Got a flimsy spherical balloon, so a sphere like a ball. It's going to pop when the radius reaches 3 centimeters. So this is referring to a radius. Assuming the balloon is filled with helium at a rate of 15 cubic centimeters per second. So that's a rate. We've got that rate. Calculate how fast the radius is growing at the instant it pops. Okay. So with a balloon, it's not area, it's volume. Okay. And when they're pumping in some sort of air or some sort of gas, helium in this case, that's how the volume is changing, right? So this part here, this rate, is the rate that the volume is changing over time. So that's our dV dt. Okay. How fast the radius is growing is the question. So what we're expecting now is that we're going to have dr dt somewhere, and that's what we're going to solve for. So you can kind of see how you set up. They gave us one rate, they didn't give us the other rate, that's the one we want to find. So when we take the derivative. We've got a fixed rate, and that is for the radius. We're looking for when r equals 3. So here's a fixed thing, and let's see if we have enough information. They give us the formula that we will need to use is volume equals 4/3 pi r cubed. And again, that's just a fact of nature. You won't have to memorize it because they give it to us here. If they give you a similar question on the test, they will give you that formula. We're not going to expect you to memorize it. Okay. It's not a geometry class. We don't use it that much. So now we've got our function, we've got our formula. We've kind of identified the values that they gave us. They gave us a fixed value of r equals 3. They gave us a rate of the volume, and we're looking for the rate of the radius. So we got our 2. What do we do first? Take a derivative. And remember, this is with that invisible time variable. So the derivative of v is 1 with the marker dv dt. So we're taking the derivative of variable of volume with respect to time. And that's something they gave us. 4/3 is a constant multiplier. Pi is a constant multiplier. So those guys just kind of hang out. R is a variable. I take the derivative of r to the 3rd power, and what do I get? I get the 3 coming down, so I'm going to move that out front. And then I get r squared. So that's its derivative. But again, implicit derivatives, right? That's the derivative of r with respect to time. Okay, and again, t is just, it's invisible, but it's in this, it's in the whole story. What can we do now? We could simplify a little. 3 divided by 3 is going to be 1, so that's out of there. And then we can start coming up here. What do we know? Well, we know that dV dt, the rate of the volume, is changing 15 cubic centimeters per second. That's 15. We've got 4 pi OR. They told us when the radius reaches 3 centimeters. They said when r equals 3. So we're going to plug in 3 for r. We're going to square it, and that's dr dt. And now we're going to do the arithmetic part and then divide so that we've solved for dr dt. So we get, what's this going to be, 15. 3 squared is 9. 9 times 4 is 36. And I'll leave that as pi because it dr dt. And then just to finish solving, we divide by 36 pi. Divide by 36 pi. So we get our final answer is that dr dt equals 15 over 36 pi, which is, I mean, it's a correct answer. And again, on an exam, you'd get full points for leaving it just like that. But I'm just kind of curious, how many centimeters is that? You know, I don't know. This is a radius. I got this far. It seems like it'll probably be less, you know, a little bit. So 15 divided by 36 pi oh, they want it to 2 decimal places, so okay. I get 0.13, 0.13 centimeters. That's the rate of change. And incidentally, on the exams, I think if you look over your last ones, if you had a correct answer and you kept going, sometimes I'll circle it and I'll say stop here, and I'll just cross out your extra work that there was a mistake made, and I'll give you full credit. So if I see the correct answer, and so say you did this, but you somehow entered it into your calculator wrong and got a wrong answer over here, I'm going to say, oh, this was correct, forget about this. Okay, so I'll do that. Questions on this one? Yes, sir. Pi, it's 3.14, or it gets absorbed. So it's 36 times that, 15 divided. It's all incorporated into here. So remember, pi is a number. It's 3.1416. It's just a long decimal expansion, infinite actually, not just long. But if you, yeah. So, and what I did is when I divided, I put a parentheses, because I think if you just do 15 divided by 36 times pi, that might be treating pi up here. But I put a nice parentheses around that when I divided, just to make sure it's all down here. Okay. And I think this is the last one. Again, this is another problem that is in the homework. Now, unlike, we did some of these with average cost functions, but remember what they gave us was the cost function, and we had to come up with the average cost function. We had to divide by x. In this case, they're already doing that for us. So be careful. On the test, you might see one from both sections, and they might be talking about the average cost function, but they might be giving us, how do we know the difference between the cost function and the average cost function? This little line tells us this is the average cost function. If they give us c of x, this is just the total cost function, right, with no bar on it. So just watch for those little details, okay? So this one is the average cost function. They've already done all the work for us. They've divided it by x. And so this one, in fact, actually, when I looked at it, I said, well, why are we even doing this? Because all we got to do is, it's like just two variables. But what makes this different is that they are, that this function is happening over time. It's the weekly manufacture. So time is now an invisible variable. It's not just, I guess usually they'd always have it over some time period, but X is the number of players manufactured in that week. So this is, again, we've got a time feature going on here. Weekly production is currently 4,000 players. So that's X. It's increasing at a rate, remember, so look for that word rate, of 400 players per week. What is this number? This is dx. It's how the number of players is changing over time. Okay, so you've got to, when you see the word rate, you know that that is a derivative. Okay? And in this case, we don't have to come up with the function. They gave us the function. Okay, so we just rewrite this thing. The average cost function is 100,000 x to the minus 1 plus 20 plus 0.0006x dollars per player. And what we're looking for, what is happening to the average cost. Now it's a little vague, but what's happening to average cost, how is a more accurate question is, how is the average cost changing over time? We know how the production is changing over time by 400. We know how many we've got. What they want to know is what's the change in the rate of the average cost. Right? And average cost is a variable, so what they're looking for is DC bar over DT. That's what the question's looking for. So in this case, when we take the derivative, we start over here. What's the derivative of C bar? Average cost function. It's dC of x, if you want, dt. So it's the derivative of the cost function over time. Think of this as our y value. So you could just, it might be easier just to say it's dy dt without all this. In fact, I'm going to take this of x to kind of get it out of there. It's just, it's the average cost function. It's the derivative of the average cost function. On the other side, we take the implicit derivative. So what's the derivative of x to the negative 1? Well, the negative 1 comes down times 100,000. Subtract 1 from the exponent, so you're going to get x to the minus 2. And we took the derivative of x with respect to time. Right? So just this is implicit derivatives. What's the derivative of 20? It's a constant, it's a number, so its derivative is 0. So we don't even write it down, right? That's gone. And then what's the derivative of 0.0006x? 0.0006, and we took the derivative of x with respect to time. So we just got to remember to put that's not just 0.006. Actually, I made that mistake because I thought I better work through it because it was going to be a little dicey. So we've got that. Now, do we have everything we need? Well, we look up here, we're given that x equals 4,000, so we do have a value for x. And we're given a rate dx dt. So yeah, we have everything we need, and we've actually already got it solved for the derivative of the average cost. Okay, so let's go ahead and plug things in. The derivative of average cost with respect to time is negative 100,000 times, this is x is 4,000, oh man, I think I may have squared. I think I forgot to square it when I was working it this morning, but anyway, squared, right? Sorry, to the negative 2. But I think I forgot to do that part. What's dx dt? It's the derivative of x with respect to time. That's the rate. We were given that currently is 400. And over here we're going to have 0.0006 times 400. Now you could also have done the algebra and factored it out, or but we've got all the stuff now. We just got to calculate this number, right? This is all arithmetic now. So negative 100,000 divided by 4,000 squared times 400, and then this. Let's maybe work it in pieces. Let's see, negative 100,000 times 4,000. Raise it to the negative 2 power times 400. I got that this first part here is negative 2.5, and then this part over here, 0.0006 times 400 is 0.24. So negative 2.5 plus 0.24 come up with that the average cost over time at this particular one ends up being negative 2.26. So it's costing so the average cost is dropping at this point because we're making more. So we should keep making them, because every time we make one more, our average cost goes down by $2.26. If I got it all right. If I didn't make any errors, which is always, and again, I don't make them on purpose. Literally, I don't. but they do happen. Because I'm trying to just think my way through here, trying to give you that experience of finding your way through the confusion. Make sense? Kinda?
Yeah.
Okay. It's a lot, it is. And that's why I wanted to kind of get you started ready, start working on this stuff, but connect it back to 11.6. Maybe work on those two sections together if you're going to go back at it, because they're related rates, right? But you'll see that that's what it is. Also, remember, I've got some solution videos for each of the sections now for the exam review, and that's also helpful because some of these questions may be in there. And then I've also got that review of when we had a WebAssign review assignment, they took it out because nobody was doing it anyway or something. But there's 40 questions in there. You may find some of these questions actually worked out in a video format that might be helpful. Okay. So, but from here on out till next Monday, we got a whole week to get ourselves ready. And again, take a step forward, do better than you did last time, or as well as you did last time. That's what we want to kind of see progress, keep going, moving forward. Monday's the exam. So Wednesday's review. We got the weekend. The final, someone else, is the week of finals week is Thursday night at 7:30. They do a common final. So I guess you guys are better. My Tuesday, Thursday will be at the same time, but they're a 7:30 in the morning class. They're going to have to take the final at 7. Every 210 takes it
That's a
Thursday
third
night.
exam.
Actually,
It's not considered a third.
I don't think so. I think we have a third exam coming up, and then it's comprehensive.
So do we have,
Well, not really. They call each of these midterms 3 midterm exams and a final. But we have 3 exams. Questions, comments? We good? All right. So we still got time. I'm here. If you've got questions, you want to work through things. If you want to take off, take off. But we've got all these resources. Make use of them.